All right, hello and welcome again. We're back here with our Crystalline Silicon Solar Cells lecture series, and I am Edward LeBeau. Here today we're talking about operation of silicon solar cells, part 2. Yesterday, or our last lecture, we did part 1. But before we jump in, let's get our joke of the day. What do you call Batman skipping church with no question mark at the end for some reason? Christian Bale. Haha. Very good. Now let's jump into our outline. So first things first, we're going to talk about open circuit voltage. If you remember in our last lecture, we talked about short circuit current. Remember, we want a high open circuit voltage and a high short circuit current to get a high power output. And remember that fill factor thing we were talking about? We want all those to be high. Then we'll talk about contacts and resistance, not as in the contacts in your phone, but contacts as in the metal on photovoltaic cells. That's where you want your excited electrons or holes to go to, your excited electrons to the front and your holes to the back. So that way you can collect them and use them as power. And then we'll talk about reflectance, which is really just light hits your solar cell, does it bounce off or does it get absorbed? But before we do that, let's remember our 3 types of recombination. First is radiative. Remember, that's your electron gets excited, it takes too long to collect it, and then it de-excites and releases a photon or a phonon. And then we have Shockley-Reed-Hall, SRH, which is due to defects. Remember, some of those defects are intentional because we need to dope the silicon. And then we have Auger, which is when we dope it a lot. And we have multiple electrons in the conduction band. They interact. One electron gets shot to a higher energy state, the other electron drops back down, and then you lose this energy as thermal energy. So let's look at open circuit voltage. So the big thing to know, well, this is a fairly complicated thing. We have a thing called quasi-Fermi levels, which we're not going to dive into. But if there's a big gap between your quasi-Fermi levels, you'll have a high open circuit voltage. But the thing to take away is if you have a higher doping, generally that leads to higher open circuit voltage. Now if you look at that graph on the right, you don't just keep doping and doping and doping and have a higher open circuit voltage, because it falls out. Remember also, as you increase your doping, your Auger recombination also goes up. So if you look at it, there's a happy medium of open circuit voltage. But also look at the negative side effect. As I dope more and more, my diffusion length goes down. And remember, we want a very long diffusion length, so that way we can have a better chance of collecting excited electrons or holes. So there's a delicate balance going on here, where we don't want to have too high of a doping density, but we also don't want to have too low. So also you're going to begin to realize there's a lot of delicate balances with solar cells. Excuse me. Next, we're going to look at carriers inside of solar cells. So if you look at it, the red is the base, the blue is the emitter, there's metal fingers on the back, and there's a rear contact. There's metal fingers on the front, and there's a rear contact on the back. So if you look at it, electron-hole pair gets excited, it travels up through the base, laterally across the middle, and into the fingers. So there's different resistances in there. We call those parasitic resistances. Parasitic resistances reduce your fill factor and sometimes have a negative effect on your short circuit current and your open circuit voltage, which remember we want both of those to be high. And there's 2 major types of parasitic resistances. There's series and parallel. And if you look at it, your series resistance is due to the resistance of your base, your emitter, your fingers, and your bus bars. Your bus bars are just thicker metal fingers, if you want to understand that. Your parallel resistance is the resistance across your excited electrons and your holes. Now, you want to keep them separate, so your parallel resistance, or your shunt resistance, you want to be very high. Otherwise, you're just going to short and lose all your energy. Now, your series resistance, you want to be very low, because that's the stuff your excited electrons or holes has to travel through to be collected. So the first one we'll talk about is our sheet resistance. So carriers in the emitter, so they get excited, they're in the emitter, have to move across the sheet to a finger. So how do you find your sheet resistance? Well, it's the resistivity of your bulk, which is basically a volume resistivity, or ohms per meter squared, ohms meter squared per meter, which is, if you want to think of that a little more clearly, it's your resistivity for an area. It's a little complicated. So basically your sheet resistivity is your resistivity of a square, ohms per square, which is your bulk resistivity, your bulk resistance over your thickness. And another way to look at that, and you see in that bottom equation, to the far right, 1 over Q mu NdT. So Q is your charge, mu is your mobility, Nd is your doping density, and T. So you want a low sheet resistance. So if you increase your doping density, your sheet resistance goes down. But remember that has negative effects with your recombination. So remember, we're at this delicate balance again. And also remember, there's your thickness. You don't want to be too thin, T, your thickness, too thin, or as we spoke about earlier with your absorption coefficient, you're not going to absorb things in your solar cell if you're too thin. So there's all this delicate balance going on. So another resistance, remember, another series resistance that we mentioned earlier was the contact resistance. So that's basically the resistance between your N-type emitter and your contact. So you want that to be very low. And your contact resistance is given by your specific contact resistance, which is the two material, that's a innate factor of the two materials you're putting together. And then A, your area. So if you have a big area of contact, you have a lower contact resistance. Another thing to know is there's an amount of energy that takes to jump from the silicon to the contact. If I have a very high doping, remember that changes my energy band, then I'll have less, there'll be a lower energy jump to get from your emitter to your contact. So sometimes you'll dope very heavily right underneath the contacts. So that way you have less of an energy jump there. But then again, remember the negative effect of doing an excessive amount of doping. The balancing act continues, right? Another piece of series resistance is the resistance inside the finger or the bus. So what's the best way to handle that? You get a very tall and narrow contact. So if you have a very wide contact, all that area gets shaded and can't produce energy, right? Light can't hit it because it's got a metal contact on the top of it. So you go narrow and tall. That'll reduce your series resistance inside your contact. So that's it for contact. That's it for resistances in contacts. So now let's look into reflectance. So there's a thing called ARC, anti-reflective coating. It's a transparent dielectric film that has a very specific refractive index. Your refractive indexes determine how light will bounce off of your solar cell. And the whole reason you have it is to reduce reflection. And reflection is reduced by a thing called destructive interference. So let's look at this. So light shines in. Either you're going to go hit the solar cell right away, bounce off, or you're going to go through an anti-reflective coating, get bent, and then hit the solar cell and get bent again. Now we prefer that none of it bounces off. We just bend the light the way the light is traveling very, very little. And if you look at this, N1 is your index of refraction of your anti-reflective coating. N0 is of the air or of the glass that your silicon is modularized in, the casing your solar cell is in. Excuse me. And N1 is the silicon. So to get the minimum amount of reflection, we want N1 to equal the square root of N0 and N2. And we very carefully design our anti-reflective coating to have that very specific N1. We know N0 and we know N2. Silicon has a specific refractive index. So does the glass we put above it. So now the one we play with is N1. Now you don't want to have way too thick of an anti-reflective coating because it does also absorb light in it. It is transparent, but nothing is perfectly transparent. So you have another delicate balancing act going on. Another way to reduce your reflectance is a thing called texturing. So basically you dunk your silicon in a vat of KOH, NaOH, and you etch your solar cell. And basically what happens there is you get all these little pyramids that get built up on the solar cell. And what happens is, so let's say I have a pyramid here and a pyramid here. Light comes in and it hits this pyramid and let's say it reflects. Okay, it reflects. Oh, well there's another pyramid right here, so it hits that. Let's say it reflects again, bounces again, right? So it bounces around inside those pyramids. Now eventually it can bounce and come out, right? Depending on the angle of the pyramid and all that. But the more times it has to bounce is another opportunity for it to be absorbed. So that's the goal with texturing. So, but before we finish things, let's do a quick little bit on efficiency. Remember, it is important to have a high efficiency. So this is the basic efficiency equation. FF is your fill factor, ISC is your short circuit current, VOC is your open circuit voltage, PN is your input power. Remember, it's the ratio of your output power, which is FF, ISC, VOC, over your input power, PIN. Excuse me. So how do we increase our short circuit current? Well, we reduce our reflectance, we reduce the energy to jump the gap, we increase our minority diffusion length, and we increase the minority diffusion length of electrons and of holes, right? A long diffusion length, a long lifetime, better chance of collection. We also reduce our surface recombination velocity, which we're not going to go into too much. And then also XJ, which is our junction depth, is another important thing. If you have a very deep junction, you're going to have to travel. Your excited electron holes are going to have to be traveled even more. And by that I mean you have your p-n junction. Do you have a really thick emitter, really thin emitter, something like that? How do we increase our open circuit voltage? We want to up the energy of the gap. Remember what we were talking about with the doping. So we increase our doping, right? We want to, just like with short circuit current, we want to increase our diffusion length of electrons and holes. That's always the case. High diffusion length, high lifetime are both good things. And then what do we do to increase our fill factor? The big thing, reduce your series resistance. Your series resistance has to get down. That has the biggest effect on your fill factor. So again, let's take a look at that equation. Efficiency is your fill factor times your short circuit current times your open circuit voltage over the input power. This is a good slide I'd encourage you to spend a little time with, really look at it, review it, because it really tells you what's going on in the solar cell and how to get a useful and effective solar cell. And that's it for this lecture. Hope you guys have a great day, and hopefully I'll see you soon.